Good evening, everybody. It's good to see a good international crowd with us online tonight. And all of you joining in the future, you're also very welcome. I just have two notices before we start. One, the European Conference on Amateur Radio Astronomy, we've now set the date and things are moving forward. We hope to have formal registration open in January. So keep your eyes open on the forums and we'll update you as that progresses. So Friday the 5th to Sunday the 6th, September 2005, the place to be. Next month, we have a newly qualified PhD student. We like to encourage students, undergraduates as well, but next month, we have a newly qualified PhD student from Bristol University. And he's, I've just lost the title of his talk. Has anybody got it in front of them?
Yes, developing and deploying an instrument for measuring ionization in the atmosphere. Yeah. This is a branch out from research on cosmic rays.
Excellent. Yeah, well done, Andrew. Yes, I had it already.
Can I just reiterate for everybody a date for your diaries? Our conference will commence on Friday evening, the 5th of September 2025, and close at lunchtime on Sunday, the 7th of September 2025. A date for your diaries. Everybody is welcome from wherever you would travel from.
Absolutely. Yeah, thanks for that.
The venue is the Harwell campus in Oxfordshire, home of Diamond Light and ISIS, amongst other major UK science experiments.
Indeed. And tonight we have Professor Xiaochun from Georgia State University, and he has very ambitious objectives with his experiment. And I'll hand over to you, Xiaochun. Our monitors are yours this evening.
Good evening and good morning or good afternoon, everyone, all the friends. Very first, I would like to thank Paul and Andrew for inviting me to share some of our stories with you tonight. So let's get started, and I'll try to share my screen. Okay, I hope you can see the screen. In the meantime, I want to make this presentation as informal as possible. So please interrupt me any moment you have questions. Then I'm definitely going to leave plenty of time to discuss whatever question you have, and at the same time, feel future. So I think this is as Paul said, this is really an ambitious and a long-term project. So I do look forward to see opportunity to work with each of you. Okay, so not sure the audience here, so let me just say a few words about the cosmic ray. Of course, the cosmic ray existed long before the life was created on the planet, and it is discovered back in 1912 by Victor Hess, as an Austrian-American physicist. And of course, this is indeed a major discovery, and he shared a Nobel Prize in 1936. And since over the course of those periods, the study cosmic ray become a major tool to explore the structures of subatomic particles. So, now we know the cosmic particles typically classified as two categories. One is a prime ray. Those are mainly originated from a galactic event, supernova explosions, so study those highest energetic cosmic particles itself is a very important branch in astroparticle physics community. To help to understand the characteristic features, the evolution of our universe, and the processes which generate those high energetic particles. Then there's also some cosmic particles we receive on Earth also coming from the sun. Those are what we call it the solar energetic particles, and pretty much connected to the solar activity, solar flares, which has important implications specifically to, for example, the our could damage our communication system and also influences space travel. Then there's a secondary cosmic particles which I specifically focus on the particles which produced by the incoming primary particles in the atmosphere. So that is where we try to measure. Okay, this is what I have been on and off for past 20-some years worked on this project. So let me move on and okay. So at the Georgia State, we have been working on cosmic project for quite a while, and this is in parallel to our research project at the Berkeley National Laboratory. And most of the effort in the early days is really focused on recruit talented graduate students and focus on STEM outreach. So generally, we classify our cosmic project into applications into 5 areas. One is monitoring the space weather activities, mainly monitoring the activities which the sun, which impact the changes of cosmic flux we measure. And also we have an interest to use the cosmic as a proxy to understanding the changes in our atmosphere, because this is also very important to everyone on the planet, because it's the atmosphere literally as a shield to protect us from the radiations. In the meantime, the atmosphere also, gave us the wonderful 4 seasons most of us experience. And the other part of applications related to the cosmic measurement is related to what I call the origin of life, or public health. For example, given the extensive cosmic radiations in the atmosphere, the cosmic ionization of molecules in the atmosphere can have an impact and to public health, and maybe even for people who often fly on airplanes quite a bit. Then moving toward the technology sectors, cosmic particles also used for tomography. Both use muons and neutrons, and we do have an interest in this. One of the specific examples is we do have detectors. We measure the cosmic neutrons, try to study the soil moisture. And the very last but not least is the STEM outreach. So this is an area we are going to focus on. So what I plan to talk today is divided into mainly 3 parts. The first, I'd like to introduce we call the G low cost collaboration and network. And then mainly focus on, because this is what Paul and Andrew asked me to do, so describe a little bit more detail about our detector. I know most of you, also making the cosmic watch, detectors. I think we could definitely share some of our experience and knowledge. So I spend more time on it. I leave a lot of, more time until the end to discuss or answer any questions you may have. All right, so unless you have questions, let me start from the part 1. This is what we call the G low cost network. As the word said, the detector, and one of the main motivations we want to build our detector is to make it low cost and portable. And for the reason I'm going to share with you in the following slides. So, so what we are really looking at is as I mentioned earlier, we are experiencing the cosmic particles, traverse the solar system and get to the surface of Earth. So during these processes, over the course of a cosmic ray particles reaching to us, it influenced by solar activities. You do see, it's well known 11-year solar cycle modulations of primary cosmic particles we measure on Earth, and also have a diurnal variations. Once the cosmic particles reach to the top of the Earth's atmosphere, typically around 20 kilometers altitude, and then you can produce the cosmic showers we call the secondary cosmic particles. So this is what our strategy is. Because of this modulation, both in the solar activities and spherical changes, we use the flux measurement of cosmic flux, so we solve the reverse problem. So hopefully we can, by studying the variations of cosmic flux change on the surface of Earth, so we can understand and monitor this solar activity and the weather. So in generally, this is classified as two parts, and we want to develop a project for monitoring the space weather and our torrential weather, which I think is very interesting, because I think especially torrential weather, we are talking about climate change, global warming, and the atmospheric changes are very sporadic, and so we hope we use this broad network to capture the features in the event so we can understand. Any of the project not such big requires a large team. So I am fortunate to be able to assemble a interdisciplinary team at the Georgia State. This is the top role. So we have 3 nuclear physicists, 1 computer scientist, we have a condensed matter physicist, a solar physicist, we have a IT managers from our school. We also have a faculty member, specifically Natalie King. She's in education, College of Education. So, and then at the same time, we do have now in our collaboration, we call the 4 regional coordinator, and started with the Professor Babatunde Rabiu. He's our African coordinator, trying to identify site and expand the network in African region. And then we also have a Dr. Nikola from Serbian, who is the Physics Institute in Belgrade and in charge of developing the network in European region. And then we have 2 members in East Asian, Upo from Sri Lanka, and also Professor Tiansun Wei in China. And this network is really growing, and especially in recent years, recent months, we start apply for a major research grant and try to build the network. So we now recruited space scientists from Argentina and Colombia. So get our detector in South America is very interesting, because this is a region we have could be called the South Atlantic anomaly. So building our detector is a really interesting, a great opportunity. So it is a long journey to get to the point. And the picture here shows the existing running detectors in our network. And of course, we have quite a few detectors running on our campus in Atlanta, Georgia. And then we also have a detector in California, which is located at Chara. Some of our astronomy friends are probably aware of the Chara facility. It's probably the world's most powerful interferometry facility to understand the size of the stars. And then we also have another detector in the Apache Point Observatory, and those 2 detectors on those high altitude become very, very important for capture the sensitivity to the space weather. So one of our goals really was to put our detector hopefully, if we have funding, put detecting in every observatory around the world. This is, I think it's a great opportunity. Then back to the lower altitude, we have detector in Colombia and Santa Marta, Colombia, where one of my graduate students came from. So we had one detector there. We have now 3 detectors in Sri Lanka. We also interested to explore, because one of the interesting regions in Sri Lanka, for example, is low gravity. So amazing, interesting nature phenomena. So we like to expand more detector in Sri Lanka to look at the oceanic atmospheric properties. And closer to it, there's also a Singapore. We have detector in Singapore, and we have detector in first deployment in African continent is in Nigeria, and then we also have 2 detectors now in Serbia, Belgrade, Serbia. So so the hope that we have more folks involved, and I think the future of the project is we want to make a data driven decisions. So the more data, and the better. So I think the detector we now our baseline design. I'm going to go over this a little bit in detail. Actually, you have one here, so you can actually see this is really portable. I can use one hand to hold the detector up, and to assemble the detector is relatively easy. Right now, it's pretty much in charge by one of my 2 graduate students plus a number of undergraduate students. So the main component of a detector is a scintillator. You see the upper right, where the scintillator design, it's the 20 centimeter by 20 centimeter, has the wavelength shifting fiber embedded on the surface. Then fiber guided the scintillation light to the silicon photomultiplier. So I'll comment to this later, why we pick the silicon photomultiplier. The bottom line is make it cheap. And of course, this is a very important, especially we want to build more detectors. Then at the same time, we wanted to increase efficiency. That is the reason with the optical fiber is very important. And this design is actually inspired by my experiment at the Berkeley National Laboratory called IcePhoenix. So we spent about closer to 10 years to develop the major accelerator experiment. So the technology has been well tested, and we simply took the advantage of the major experiment applied to our cosmic measurement. Then the other work, which most of you probably experienced, anytime you build the particle detectors, readout electronics is always a headache. And this is one we spent a decent time, probably over 5 years, over the course of 5 years. So at the latter part of my talk, I'm going to show, selected a few versions of the readout electronics. And you see here on the right, this is a small circular board. This is I call it the version 2, which has 8 channels plugged into the Raspberry Pi GPIO pin. And then pretty much this is a regular Linux computer. You can log in, you can configure and run collecting data. So for this design, we try to optimize the physics we get plus the cost. So, for single layer detectors use SNPM, you have a lot of noises. So that is basically noise wash out some signal. So we made a 3 layer, and so for example, in this picture here, we record the muon hit coincidence between top 2 layers. So anytime you have particle hit top layer, middle layer, we record. We record every minute, how many during this minute, how many instant. This time duration can be changed, configured. And then same time we record the bottom, middle, and the bottom layer. So this design gave us 2 advantages. One is the reduced noise. At the same time, it's self consistent checks, because statistically, as cosmic particles suddenly, constantly shower down from space, statistically, you should expect the same amount of coincidence from top two layers and equal to the coincidence on the bottom two layers, because they're same size, separated equal amount distance. So, this is one thing we always check. And then at the same time, if you really wanted to look at the narrow cone of the atmosphere particles, you're looking for coincidence between top layer and middle layer. So give you a natural, narrow acceptance of a cosmic coincidence coming from. So this actually, shows a stronger correlations with atmospheric pressure change. So we do have a published proceedings in one of the cosmic conferences. We presented our initial design. And the main message is the cost much cheaper than the iPhone. So people can afford the iPhone. I think making one detector available, it's very doable. Okay, and at the same time, it's very portable and easy to install. So once the detectors, it's a shift to the side, plug to the power and the network, and then immediately the data gets streamed to our server and Georgia State. So let me maybe pause a second. Any questions before I move on to the next slides? Assume, Paul, you hear okay? Good.
Yeah, we can hear.
Okay.
I do have one question. Why
Yeah.
13 centimeters? What was the rationale for that Z spacing?
Good question. We had earlier version, and it's a 15 centimeter by 15 centimeter. And the initial version we actually built 3. So when I gave a talk at Oak Ridge National Laboratory, and then my friend is sort of confiscated the detector. He doesn't want to give the detector back to me anymore, because he actually used the detector to monitor the reactors at Oak Ridge. Amazingly, our 600 detectors monitor the reactor activity as well as the, I think, 20,000 detector. So, but for the cosmic measurement, statistics are very important, right? So if you look at on average, you have assuming outside, you have one cosmic particle hit the some nail size, 1 hit per minute. So you can estimate how many cosmic particles. If you take the statistical uncertainty square root n, smaller scintillators, you have large uncertainties. So we wanted to get it to the point we're looking for 1% statistical uncertainty. So 20 by 20 centimeters roughly give you that statistics. Certainly the better, larger the better. Then you get to the point, are you able to efficiently, uniformly sample the particles in every part of the scintillator? So that is how I come up. So we actually have a simulation. I have pictures to show.
But Paul, could I ask a question here?
Yeah.
Thank you for the description of the size of the detector. I, like many others on this call, will probably have a pair of the Cosmic Watch detectors, and just calculating off the top of my head, I think your data rates are going to be at least 2 orders of magnitude greater than ours. And I've been thinking about the statistical precision of
Yes.
what could be doable. I mean, the Cosmic Watches are great fun, but they are tiny.
Yeah.
My guess, I'd need to sort of measure for an hour to get a 5% measure. You can argue about the geometry, but that's a separate question.
Yeah. That's exactly the reason. Yeah.
Yeah, and I can see the need for a much greater, much bigger size. Just to clarify one point, I'm not sure I heard correctly. When you said you wanted to narrow the field of view, do you use the top detector and the bottom?
Yes.
Right.
So
Okay.
we have 3 coincidence.
Yeah. Sure.
Top, middle, and middle, bottom, and the top and bottom. So this is a 3-layer detector.
Yeah, but the top and bottom are going to give you a narrower acceptance.
Yes,
So,
it's typically based on this design, we simulation and measurement. You see coincidence rate is typically about half. Top or bottom is a half of the top and middle.
yes, okay, that's just due to the geometry.
Yes, due to
Yeah,
the
okay.
coverage of
What what time resolution are you using here?
We record. Well, those are readout electron typically around 50 less than 50 nanoseconds. So basically that is where the coincidence get calculated in FPGA chip, right?
Okay.
So because we are not interested in tracking individual cosmic trends, we statistically will look at what flux change. So we record, given this 1 minute, how many counts every time you have a hit, I record it until reach to the minute, reset.
Yeah. Okay. I'm thinking in terms of what I can do with the Cosmic Watch. I've spent quite a long time this year looking at the code and thinking about the nature of the electronics and the effective time resolution. You can argue about the details, but it's of order a millisecond, give or take a factor of 2.
Yeah.
There's all sorts of weirdness going on in there, which I still don't understand.
Yes.
But
Yeah, I think some microseconds level that's probably okay because of the sheer number of particles coming, right? So the only problem is people. I think you might have heard people use uh, 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 the uh, the watch, not the Cosmic watch, the MIT based. So some of the uh, uh, camera. So we look at the pixel hit because those are great exercise. You can measure the particle hits, but the question is what you get. Is the measurement statistically meaningful for the
yeah,
interesting measurement? And for the education, it's great.
I absolutely agree, and it's been at the back of my mind just how much effort it's worth putting in to do anything too
Yeah.
heavy with the Cosmic Watch, simply due to the fact that we could not come even close to competing with this. It would just disappear into the noise. Yeah.
Well, I think the conclusion we reached to this point is not overnight. We spent a really good over 10, 15 years to reach to this point. It was a long journey.
Yeah. No, I can understand it. And in order to pin down the physics longer term, I can see the need for
Yeah.
something like this. Yeah.
Yeah.
Thank you very much. That's very interesting.
Okay. Good.
Can I put in a question that's
Okay.
appeared in the chat? AC is asking about the purpose of the wavelength shifting fiber. I was going to ask the same question, so somebody else got in first.
So wavelength shifting fiber is very because we for the scintillation light. Latter part I'm going to show typically traditionally for past more than half the century people use a vacuum Foley multiplier. So then you needed to design a light guide to attach to the scintillator and push the scintillation light through the light guide hit the photomultiplier. Those photomultiplier may be 1 inch diameter, 2-inch diameter, depends on whatever you have. So it's very expensive. So now we use SNPM. SNPM is a solid state silicon photomultiplier. So the sensitive SNPM is about, in my ice phoenix experiment, we use a silicon photomultiplier 3 millimeter by 3 millimeter. So for this detector, I'm using 2 millimeter by 2 millimeter photon sensors from Hamamatsu. So now that means you need to guide all of the scintillation light from your scintillators towards the SNPM. So that is where the fiber needs. That's one point. There are two. Second reason is you loop the fiber that way, so you can sample as uniform as possible the scintillation light produced in this 20 by 20 centimeter area. So they have to go in through all of the optical transport and get into the fiber through internal reflection and then reach to the SMPM. Yeah.
Thank you.
Yeah, and it's just a matter of a cost, and I think this is technology we adapted from S-Phoenix experiment at the Berkeley National Lab.
Could I ask a quick question, please?
Of course, yeah.
Yeah, you explained briefly earlier about how you're getting the analog channels from your SIPMs into the Raspberry Pi. Could you just explain that in a little bit more detail, please? The sort of the acquisition rates you're getting per channel, and are they? And does the Raspberry Pi Linux, is that a hindrance at all? Because it's not really classed as a real-time operating system, so you are going to suffer occasionally for when the operating system decides to do other things. So how are you addressing those issues?
Okay, so I will get later a chance to show the circuit board.
Okay.
Yeah, so I think we'll get to that point. I'll explain a little bit more detail.
Brilliant. Thank you very much. Okay.
Good. So let me move on. I don't want to keep you up all night. So so you may interested, what do you get, right? This is where on the left you see, we actually just end of last year or beginning of this year published our paper in the Space Physics Journal, mainly based on the detector at the Chara array, very high altitude. And we also compare our results with the ULO, which most of you probably are aware of. It's a neutron detector located in Finland. So, so this is typically a weekly report, which my graduate students prepare. So a group meeting. So I just took one from his report, I think a week ago. And each panel shows each of the detectors. You see the top three, those are the detectors at the Georgia State on our campus, located 3 different buildings. And as you would expect, they should be behave identical pretty much, right? You see the trend goes up and down. And then the 4th and 5th, those are high altitude in the Chara. Then we also have a detector here, if I read in Serbian, and we have a detector in Sri Lanka and Singapore. So our detector basically spit out the time series of every minute. And for this plot, we make hourly counts. So typically you accumulate 1 hour counts and you calculate the average during the period and calculate the percentage change. So then you notice that the plot you see here, it has the green lines. Those are historically been verified as the pressure change. And you see the perfect anti-correlation with atmospheric pressure, right? And then you notice at the bottom two, the detectors near equator, and the pressure changes not much. This is an area we wanted to really, looking for opportunities. That requires more work to do, is to see, given the weather patterns in different regions, so how can we develop a data model to, understand the atmospheric properties in real time. Real time is on the hourly or minute level, snapshots, from all detectors in 1 second. So it's great to see. You also get to see the precision we talked about earlier. This gives us a sensitivity to the atmospheric properties, right? So, so this is what we current plan. So we want actually have a broader measurement in parallel. And the very first part is the build ground network. That is what I showed the previous slides. Then at the same time, we also interested in measure the radiation in the air. And I'm going to share a couple of slides which I took because the detector now it's very portable. So just to make it scintillator smaller, that's because this is what I have been carry the detectors, even detectors running can pass through the TSA checks. Sometimes, have issues with the TSA folks, but I was able to manage to pass through the TSA and took the detector on the airplane. And I don't think, this is probably one of the more accurate measurement of, X-ray radiation dose in flight. And also in parallel, we're interested to develop detectors put in space, is specifically a CubeSat. The reason for this one is, I think we all know cosmic particles we see here influenced both by solar and the weather. So if you put detector, in between, in space, hopefully you can help you to separate the space weather effect, so if you wanted to really study the terrestrial weather, you want to correct the space weather effect. As we all know, some places a huge role to the life on Earth, because then, of course, if any slight change of a solar may influence our weather system. And then, of course, the last part, every summer we have high school students, and those are 3 high school students, worked in our lab, I think last summer or 2 years ago. And so this is really fun. And so let me say a few words about one of the effort we're interested to do is the, atmospheric tomography using cosmic ray. As I mentioned earlier, cosmic is discovered by Victor Hess, and he loaded on the hot air balloon the detector and discovered it. So it's just some sense we are trying to relive Victor Hess' experience. So instead of flying on airplanes, I just took detector on the airplane. And this figure also shows interesting because we are typically talk about 30-kilometer range where most of cosmic shower activity is happening, and specifically around the 20 kilometers, and you see the called Fulzer maximum effect. But I think this range is constantly changing now, given the warmer temperature. So I think if we have tools to be able to monitor the changes in the atmosphere is very important. So this is a measurement which I did when I was traveling to Nigeria for installing one detector. So I flew from Atlanta to Paris and Abuja. And this was the trip actually because I wanted to record the real time. As some of you know, the Raspberry Pi does not have a real time. So you need to set the initial time so that you can have a track of the time. So this is the time I just turn on the detector before I leave. So I let the detector run, and when I was driving to the airport, then I went through the TSA, all of the exercise too. So it was a long flight, and so this typically happens once I get on the airplane. I took out the detector box from my backpack and put it under the seat, and you see that box there. That is one of the detectors. Use identical readout electronics, and so this is a measurement, and so you see the horizontal axis is a time and date, and you see the starting time. So no stopping. This running off the phone charger. So I have you can run for about 18 hours. So I think I have a Raspberry Pi also depends. It's a low power, computer. And so you start, the detectors, then you travel, then once airplane flies, the reason I did this is that for many, many years, especially about 10 years ago, every travel I have, I pretty much carry a Geiger counter. So this is one of my hobby. But when you use a Geiger counter, I think, cosmic watch is a great device, probably can carry the cosmic watch. When I use a Geiger counter, and sometimes harder to record the counts. So I was trying to basically literally write every count, minutes counts on my notebook. So now with this detector, you can automatically record, then you can enjoy other entertainment on the flight instead of busy writing numbers. So you do see a couple of features. So when your airplane took off, you start to see the rising of the clouds, and then when they get to the airplane descend, you see it started to back to the normal background rate. So at the gate, typically clouds is about 50. Fluctuates as you would expect, because this is about 10 centimeter by 10 centimeter centiliters. So this give you the rates. Then from airport, rest a couple hours, and then flew to Gemini. And that time my battery ran out. So once the airplane landed, I swapped out another battery and took another run. So then you get to the point that the feature is from Atlanta flight to Paris, you start to see gradual increase of cosmic radiation because it's close to the pole region. And because we know more cosmic particles in the pole region, then from Paris you fly toward the equator south, you're going to see less cosmic radiation because of geomagnetic field effect. So this is really a comfort data to prove our sensitivity to our detector to the measurement. And it is interesting. So it depends on which group we are talking about. The technology can be used for aviation industry, for example. Tried to because I think FAA has rules. Every pilot are not allowed to fly for a certain amount of hours a year. Simply because of radiation, right? So, but the question is, well, that really a hard cut or whatever, for whatever reason. So I think part of our cosmic project is really understand how the cosmic radiations influence the public health, especially maybe our flight attendant. Definitely, it's not that dangerous because so many people fly, so we don't see. The question is to what level it impact to the public health, or maybe we are benefit from it because it gives us actual radiation. And this is get to the philosophical discussion, but I don't want to get into for now. So now we have back to the Earth. So we literally started to reconfigure our detectors. And in a recent proposal we wrote, so actually we wanted to have, if possible, each side we have 3 detectors. One point vertically up, then one point east and west direction. So this is a well-known east-west asymmetry because of the Earth's geomagnetic field, and the protons are coming from is a positive charge. You do see east-west asymmetries from cosmic measurement. So this will give another reason you want to have a slightly larger detector so you can capture statistically the differences from east and west. And then just a month ago, maybe 2 months ago, so we have now detectors in high school, and we're working on put a detector in other high school. So our faculty member are going to high school just to describe what we are trying to do. We actually now connected to the space weather monitoring because of the, to keep the high school or middle school kids entertained, it's a very tough task. They may be interested in for 2 weeks or 3 weeks, but after a month, they're going to ask you, so what? You see numbers are changing, vary. So connected to real science. This is what I learned pretty much, since 2000. And so, get the students connected with a longer term, goal. And I think that is very beneficial to all meaningful scientific, STEM outreach. So, this is really, I suppose that it's a really ambitious project. And to some degree, it's really to build a network of people and with network detectors. And we do encourage and you really appreciate anyone, whether it's physicists, doctors, or meteorologists, teachers. I think help to build the network and it will be really, really important. And the data, we're going to collect years to come will be very, very, unprecedented data. So I think the, for a variety of reasons I mentioned here. Okay, so before I move on to the next part, I maybe reset here and answer questions you may have.
There are some questions in the chat. I'm just going back to the wavelength shifting fiber. Just to be clear, there's not a changing wavelength. It's only directing the light flash to the SIPM. Is that a correct summary?
No, it is actually we use wavelength shifting fiber. So scintillation light, the wavelength is a little bit shorter. So we use Y from the Curie wavelength shifting fibers, specifically called the Y11 wavelength shifting fiber, to shift the light toward a little bit of green side, so that it matches the quantum efficiency of the silicon photomultiplier better.
Okay, that makes sense.
It also plays a role for guiding the light. So we do want to shift the lights.
Yes, sure.
Yeah, shift the wavelengths.
So I mean, what is the wavelength of the light then within the scintillator?
You mean the scintillation light?
Yeah.
Scintillation light is visible toward the blue side.
And that's not true for the SIPM that you're using.
Yeah, so typically SIPM has a wavelength shift, the quantum efficiency, the peaked around between, let's say, 300 nanometer to 700.
Yeah, okay.
So the scintillation photons typically energy is about a couple of MeV, so 1 point some MeV, not MeV. Those are very dangerous light. So the electrovolts, those are from molecular. So couple of, so you wanted to slightly shift the wavelengths. Yeah.
That's clear. Okay, yeah, thanks for that. There is a question about the construction of the detector. Is this a commercial product for purchase, or is it an open source design that you're hoping people will take up and build themselves from a parts list that you can supply?
Yeah. So there's no secret about this. I think we have published our papers so my goal is we are currently impending of a major research grant. We applied from MacArthur Foundation. So we just happy passed the second round cut. Hopefully we can reach to the final. That is a $1 million, $100 million foundation grant we apply for. So for that grant, we goal is to build 10,000 detectors, freely distributed to everyone around the world to help build the detector network. Specifically focus on for example, schools, and then talk about the, so we don't sell detector. I think this is a more focus on the benefit to more broader society. So for example, we do, if for example, there are collaborators in African and Serbian. So we use the funding at the Georgia State. So we build detector, assemble, test it, and just took the detector to the location. So our host group will maintain the operation of detector. So that is something which I'm not sure whether Ashwin, my colleague here, is in a meeting or not today. So he's the one sort of in charge, working with each group. So we set up a MOU, institution MOU. So basically, GSU responsible for building detectors and ship detector to this, site. Then our collaborators on the given site will make sure operate detector, power, and network. Then we share the data. Data will be freely available, even with a request. And then, of course, the building scintillator, building one is a little bit challenge. So you have to polish the scintillator, groove the plastic. This is so the reason we were able to build now probably 20 detectors is through a contractor in Russia. So my project there, we actually ordered 14,000 scintillator. So literally, they have a factory to build the complete scintillator tile. So this is what you see here. This is a completely assembled this scintillator tile cut on the corner. So let me connect. So you may, I'm not sure whether you actually can see the fiber or not. So this also made with a 3D printed coupling, so you can couple the module. So assemble is relatively easy. So making this one, if we do get a funding, we have to contract it out for making many of those. And our physics shop here at Georgia State can make those scintillator. Just it takes time.
There was a question about the energy resolution or the energy spectrum. Are you making any attempt to determine the energy of the incoming muon?
No, and because muons can traverse the block concrete or steel. So muon passes through the scintillator. Measure muon energies, it requires extensive work.
Yeah,
so
sure.
whether it's low energy or high energy, muons will lose the same amount of energy, more or less, in the scintillator. So we cannot measure. But it's not important for us because we are interested in flux change, how this change is caused by weather change or solar activity.
You've just noted there that the physics motivators are sort of largely atmospheric and solar, if you like. Do you preserve the data with sufficient time resolution so that you could do short period analysis and look for bursts where you get deviations from exponential distribution?
I'm not sure exactly what the time resolution you're talking about. So we are, basically record every minute, how many coincidence particle hit the recording, right? So there is one idea because I call it the cosmic detector farm. So literally we can put for the hardcore a cosmic ray scientist, they want to build detectors, few hundred square meters, right?
Yeah.
And so you can reconstruct what is the most energetic part. That is not the interest of this project. So, but in principle, this detector can be configured for high energetic cosmic shower measurement. So that requires the significant change of the radar electronics.
Yeah, I think the kind of work I'm thinking of is similar to the kind of analysis that was done on the neutrinos from SN 1987A.
Yeah,
where you're looking for an anomaly that just does not fit with the shape of the expected distribution.
Yeah. So at present time, that is measure the neutrino is not my favorite thing to do.
No, I know it's not neutrinos, but I'm thinking that the same method could be applied to detect a burst of muons. Yeah. Okay. Thank you.
Okay, so maybe Paul, any other burning questions out there?
Just to conclude the current set of questions, AC is asking if there's been any attempt to utilize the copious muon data that's typically discarded from the ice cube detector.
I think I'm an experimentalist. I think if I say no use, this is against my my training. But I think I'm a fan of moving forward, because those are existing muon detectors, as you know, there's a lot of uncertainties we don't know, and because there's existing, because when we apply for grant, it's people asking, it already existed in network cosmic neutron detectors, maybe 40 or 50, and number of cosmic muon detectors. Why do you want to build your new ones, right? It is a valid question, very valid questions. Now the question is, are the data being scientifically validated? Because each detector, the different operation conditions, some of the building sizes are different, sometimes has a problem, and to revisit those data probably more troublesome than you start new detector. Of course, if some of reliable, for example, UNO detector data actually quite reliable, that is people. So the advantage of our detector is identical, and as you saw the picture. So we plant this detector every part of the world. We don't need to worry about acceptance change. We know the detector efficiency. So every change you get is automatically the physical effect. So I think this is where we needed to move forward. Getting new data, so that and then the consistent framework, and I think the get to the size much more. To me, I am biased for sure, and we get more, I think, the important results.
Thank you.
All right, so maybe I think let's move on. So a little bit of history. So I'm sort of hinting that this was not overnight work. So initially, when I worked on Georgia State, my solely goal is to recruit talent graduate student to my program. So I built a used cooking pot, literally, $30 cooking pot, sand inside, put liquid scintillator, built the first muon decay lifetime measurement, and use a vacuum photo multiplier, and use a KMAC, NIM. Some of you probably still using those equipment, and then same time we started from upper left. That is the very first group of students we worked on back in 2002 with a group of middle school, and we load up heavy equipment to put detecting in middle school, and then we pretty much move on. So over the course of 8 years, we moved to middle school, high school, built different detectors. All of those detectors, including my bottom right, that is my graduate student. We actually use the vacuum photon multiplier, use the KMAC. Readout electronics was a headache, extremely challenge. So fortunately, we through my other experiments, we have a spare, so we can assemble 2, 3, probably the most. So not to mention you want to distribute in the many. So that is one of the motivations we started to develop a detector. This is more. So then following those years, we started to we actually part of we call the QuarkNet group, developed by scientists at the Fermi National Laboratory. So they tried to bridge, middle school, high school in close to the Fermi Lab area. So we were recruited to join their effort. So then we spent probably about $5,000 to buy they already made the scintillator, so we just need to assemble, has to read out the electronics boards, and then so now those are the two examples of very non-portable. It's a much less expensive. Each one's here cost about the $6,000, and you see very nice spectrum. Vacuum PMTs are working very nicely, but it's not possible to replicate many units. So that is definitely the motivation we started working on. So around 2015, so we started to modularize our detector, improve the design. So you start to see the upper right, we started to, more or less building the cosmic muon telescope with 3 layers of design. And then we also built called the neutron cell, measure the cosmic neutrons, because I think the neutron measurement and muon has a different physics associated to it. So we developed the technique to insert the modules between the scintillator plates, so we can look at the coincidence and determine the cosmic neutrons. And this is still not in the production mode, because the discriminate neutron signals from massive muon signals is always a challenge. So so we do have an interest to work on this. So now move on to a little bit of electronics. So this is 3 versions of the readout electronics. On the left, you see the original called 4-channel. So this is where we have used the RG45 cable to connect it to this little circuit board we designed, put it on the scintillator, including the silicon photon multiplier that provides amplification signal, and send it to the coincidence units, and then they read it out by computer. Then the middle part is what I call the first version of the Raspberry Pi based. This is we have 8 channels to basically connect to the 8 scintillator channels. So then in the middle part there's a FPGA. It will the 8 channels will be amplified, and then amplified signals feed into FPGA. It does the coincidence and algorithm. Then the output of FPGA connected to the GPIO pins on the Raspberry Pi. So that means once in a while Raspberry Pi will receive an interrupt, and that is how we record to the hits. And so this does have limitations. How fast you can interrupt the Raspberry Pi and record to the counts, and so I think for the measurement we are trying to do, it's the time resolution it's sufficient for this, because you're talking about roughly about 200 counts per minute per se. If you divide it by it's, I think the interrupt time is not a impact factor. And then pretty much are now also 8 channel has limitations, because there's a limited GPIO pin ports. We can read them out. So pretty much overkill. So then we decided for the more production purposes, we went back to 4-channel. So 4-channel allows also the new port on the right. It also has a humidity pressure sensor, and so we can read out the pressure. And so this is a version we are pretty much we're going to stay for now, and the for the next batch of the detectors. It can run on Pi 3 and Pi 4 and Pi 5. A couple of words about the scintillator. So this is where I think some of you asked questions. This is how the scintillator got made. And this is, picture on the left shows the shop making the polish the scintillator. On the right, those are the scintillators we made for the CubeSat detector, and also the same scintillator I used on the airplane measurement. So you see how that fiber got routed and then efficient. This is maybe a couple of comments I want to make, because years ago, back in 2015, a couple of my undergraduate students also built a MIT-based cosmic detector, and put the silicon detectors on the face of the scintillator, and so on the without the fiber. With that design, there are some inefficiencies of collecting all of the light. And so it has to be very strategic where you put the SNPM. And detector cannot be big, and because otherwise you're not going to have efficient. Same time, we also did it with if you rotate the angle, that's not changing much, the flux change. So we definitely see the advantages of the fiber SNPM coupling, and it's really. So this may be the last one. So we also run extensive simulations. Those are, work I did with a couple of my undergraduate students, I think 4 or 5 years ago. So we have a full-blown Geon 4. Some of you know the Geon 4 detector simulation. So we simulate anything, pretty much. We have a realistic, material, budget, and understand the accept the efficiency. That is how we come up 20 by 20 centimeter design. I guess that's it. So sorry for it taking a little bit longer time than I expect, planned. So any questions? I do have one detector running next to me, 3 feet from me, been recording data for past 3 months. And we want to put this detector sometime in Massachusetts. And also, if you are interested in the YouTube video here, this is a YouTube video Georgia State made for our project. It's help us try to apply for MacArthur Foundation grant. So it's a short 19 seconds video, talk about, very, very, brief introduction about our project.
Okay, good. And the bid to the MacArthur Foundation is for the 10,000 detectors. Is that $100 million? Yeah. I was going to ask whether it was NSF you'd applied to, but it clearly isn't. Yeah.
Yeah, that's videos for the MacArthur Foundation. So for NSF, it's more focus on scientific study. So we specifically want to put detector in South American and use the east and west configuration to look at the Southern Atlantic anomaly. And one area which I think we already established our work for space weather monitoring, and we do looking for certainly we welcome everyone to help us to spread the expand the detector, then plus also understanding the atmospheric terrestrial weather. This to me I think is the equally important for monitoring the space weather. And but everybody can talk about the weather, so I have their say. But we hope with our detector we have more of scientific argument, but we'll see. And
I have a question. How far advanced is the CubeSat element of your project?
We if I go back here, the CubeSat. So CubeSat detectors, we have the detector. So only thing, okay, this is one. third. That's pretty much the detector. So we had a visit with NASA, California. So this design pretty much uses their I think 6U unit. So this is a 10 centimeter by 10, less than 10 centimeters. So we wanted to attach. So we have not, my colleague here, Ashok, so he's a faculty in computer science. So he's leading on this effort. So we have not seriously looked at, how to interface our detector with the CubeSat electronics, stuff like that. And we have not even tested with the, solar power. So this is area we do, look for collaborators. Okay. And it's, this is, I think, the interesting project to explore.
And will that be funded from the MacArthur grant if you're successful, or that will have that to be separate?
So for MacArthur Foundation, so we mainly focus on put detectors in underdeveloped regions, especially in African, South American, some of East Asian. So it's the, not, we want it to be more realistic. So MacArthur project is a 5-year and develop and launch CubeSat. I think the impact is less than, bridge the detector. I think my goal is to, climate impact everyone. And, folks in African, I had a great time when I was visiting Nigeria. I think, they need more help. And we actually learned quite a bit because, our detector, you saw earlier the pictures I show results, they, sometimes also challenge even maintain stability of electricity. And, but the cosmic particles shower down as much as in African and in UK, right? So if we can have the equipment available for kids in those regions, inspire them to join, because this is really a longer term. It's not a project we could put people food on the table next day. No, that's not. I think it's fundamentally it's a long-term education and and monitoring the space weather and the climate. That has a I think an important implication. So that is what we try to focus on MacArthur. For the SF proposal, we submitted the pre-proposal a few weeks ago. So I think I'm actually confident that we will be invited for full proposal, which is due in March. Then that's just more focus on space weather monitoring. So what basically need to understand what is the configuration of a detector in different regions of the world so that we get maximum sensitivity. So our argument is because of a geomagnetic field effect, the particles reach to different part of the world is non-uniform. It is influenced by the changes of magnetic field, which is on the hourly activity. And nobody, even NASA, I don't think they have such, coverage. And so we, our goal is not to replace the work NASA does, but provide a very complementary opportunity with the technology. Every people walk on the street can contribute.
Can I just ask a quick question? Sorry to butt in. Just going back to what I was asking before, just to be clear, your analog channels coming from the SIPMs are going into an FPGA, is that correct?
Yes.
Okay, then you're doing the processing in the FPGA, and then you're deriving GPIO outputs into the Raspberry Pi, yeah?
Yes, yes.
Okay, well, the FPGA, is that a standard FPGA hat for the Raspberry Pi?
No, we use ICE, also because of cost, so we use ICE40.
Say again. Sorry.
ICE40.
Yeah.
I think it's a very low end FPGA.
Okay, and you've programmed, or you've done the firmware for yourself.
First, so unfortunately I had to learn.
Yeah.
I refused to learn programming FPGA.
VHDL. Yeah.
So yeah, this is where my graduate students are doing.
Yeah. Okay, that's really interesting. Yeah. Okay. That's so you got how many channels?
So right now, because of channel is limited by the available GPL pins on Raspberry Pi.
Yeah. Okay.
So that is FPGA. You can have many combination of So we are depends on if we really want to build in the use this configuration for large cosmic ray.
Absolutely. Yeah.
Detectors, then you really have to time in,
This is where you're getting your real-time processing through the FPGA, and then you can offload that. Yeah, got it. That's thank you very much.
Yeah.
Fascinating talk.
Thank you. I enjoyed it.
I'd like to make a comment here, if I might. I'm Kerry Banky, N6IZW, and one of the ARIS engineers, so it's amateur radio on the International Space Station. And we're in the process of putting a pair of the Cosmic Watch detectors. It'll probably be a year yet by the time we get everything fully functional up there. But just want to make that comment that certainly enjoyed your presentation and good information.
Well, if you're ready to launch your, we can send our detector to you. That is not, and I think we really want. I think given the importance of the size, I think making a small detector for us it's relatively trivial. But launch to the space, it's literally a challenge. So
it definitely is, and because of our space requirement, I mean our physical space requirements, that's the reason that we're going to be going with the Cosmic Watch, just to be able to actually shove it into a package that it'll be inside the space station, and it will allow students to be able to track various kinds of data as far as temperatures and pressures and various gases and such. This will be something that will be available eventually for them to track on the internet.
Yeah, that's a great
That's
effort.
cool.
I all for those work and for sure. But I think the one thing needed to address is the statistical uncertainty. This is where we discussed multiple times. One of my to-do list is really one needs actually to simulate exactly what is the level of radiation at the orbit, right? So then you can estimate how many hits your detector gets, and things along that line.
Yeah, and for us too, the orientation is going to be an issue. We may not have too much say as to the actual orientation of the pair of detectors, so we may have to sort of take what we get.
Yeah, and one thing we want to do for the future version of Arena, we also want to put the accelerometer on it, so we can if a detector orient. The one given the time I have not talked about, actually Xiaochun took one of our CubeSat prototype, had a hot air balloon flight back in April. It's a fascinating results. So we very accurately measured the photon maximum. So basically, detector rise up, get more counts. Then when it reaches a certain height, the balloon popped because of less pressure. And then the detector, past the maximum, then the radiation get lower. So when detector fall back, and you start to see a higher radiation level. So that give us a sensitivity to measure the photon maximum in the atmosphere. So this is one of the potential exercise the students can do to launch our detector on the hot air balloon. I think that for this type of exercise, cosmic watch probably could. You can go up and to reach to the maximum cost when the balloon goes up, less cosmic radiation, then fall back. You measure the photon maximum altitude variation. Yeah.
Can I just very quickly chime in and say, Kerry, if you reach orbit, do come back and tell us about it.
Oh, absolutely. Yeah. I was, first made kind of internet contact through Paul Hearn, and he's a good channel, I think.
Thank you.
Could I ask a couple of questions here, or make a comment too? I've worked on some other projects similar to this that data was being collected, and then people branch off and try to make their own detectors. But I find the scientists like to stick with the detectors that were funded or that they developed. So that can be a problem. But maybe if you publish clearly, and it may be in the paper you reference, the detector, the scintillator, the material that's used, and the size and shape of that scintillator, so that people could duplicate your scintillator and then do their own thing on electronics, because there are a lot of people that have some clever ideas for the electronics to work with. But the other aspect that you mentioned was your data would be available. And I think people would be very keen to learn how to access your data, because they would want to try to correlate their readings or information with other readings that other people have. So you might comment on how to get access to the data that you have of existing systems that are operating.
Yes, those scintillator design fibers in one of our preceding paper, and the detector brief description is also in the paper published in Space Physics, and and I think the more importantly, I will be more than happy to share some of the details with anyone, and this is, I think, for a general public. I think the more people use it, the better. And so for the data access, so we do have a sort of a public portal one can access, and so right now we actually redesigned the website, mainly focused for the MacArthur Foundation grant. If you write down spaceweatherdata.org, click on that one, may have a, we are still, this is a, massively under, development. So some of the high school students start looking at, but I think we want to do, especially one of my graduate students really wanted to, prepare a detailed documentation as far as how to access, even provide the sample code. What I really meant, if I go back here, so they can make a plot. This is a plot I made when I was staying in a hotel, but more important, like those plot, right? So once you start to have a time series plot, then you can do many interesting work. You can look at your local weather, and back in a couple of months ago, we had a major weather system, a hurricane. Our detectors start along, because it's low pressure system. Our muon counts, rose significantly large. So then we are looking for any improvement So if this group has an expert on try to maybe even replace a Raspberry Pi, with a different real-time readout, I think we are very open. I'm very open. Yeah, you're muted.
It'd be interesting on your data if it's published how the data is formatted, so that people may even want to copy your data formatting process, your metadata, and then the way you structure your data, so that it's a commonality between different systems for research to help with that process.
Okay, so I can quickly let me stop sharing this window. So our data is pretty much ASCII, just one line. It's a straightforward. So let me see whether I can share. I'm going to share my entire screen. Are you able to see the screen?
Yes.
So the two screens, actually two detector running next to me. The screen on the left, this is the CubeSat detector. And you see the first column is the first layer, two-layer coincidence. The second one is the top bottom, and the third column is the bottom two. And then I think it's because the detector are very close element, so that is very similar. But the middle part is always smaller than Then the most important part, I think, on the right here, you see this is a first two layer, and the top two. This is what I would say. Typically, top bottom is about a half of the top, middle, bottom, and also you see the consistencies, with the two layers. So given the fluctuations, right? So statistically, they are pretty much identical. And data is formatted. I think this way it's easier for people to look at that. So the timestamp, you see that every minute we record. And this is it's the local time. So then when we started to do analysis, we put it to use the global, the UTC time.
Thank you.
If you do develop the plots that you've got in a Jupyter notebook, it would be nice if you could share those notebooks as well, so
Yeah.
we can.
So one of my PhD students she's actually defended 2 weeks ago. So her dissertation will be submitted sometime next week. And then one of our requirements for all our students is to document all the details they're using the notebook. So we do want to make sure the notebook available to anybody, the plots, including the code, and we use for making the published plots.
Great, thank you.
And I have one more question. I've built 3 of these cosmic watch detectors also, and I followed this stuff from MIT and how he wrapped his scintillator with a foil. But I experimented with using some aluminum paint or metal. It's a Mira paint, and I just wondered if you'd ever tried that to get better reflection from the internal reflection on the scintillator.
Yeah, so in our lab, when we build the detectors, we use aluminum foil. It's just so for this detector, this actually made in Russian, Vladimir. So this is where they cut this. They actually use extruded machine to make the scintillator that cut it. So once they cut the scintillator, they basically put the plastic scintillator in a chemical liquid to have a chemical coating. I think the material that is exactly what you're talking about. The chemical coating gives a much better reflectivity and uniform reflection. So this is a detector we now use. It's the chemically coated. Then after the chemical coating, we have a 2-layer wrapping to prevent the light to get inside the scintillator. Use the Tedlar, and then also the outside has 3 layers, then the tape. So this is, I think, the proof design, which worked very well. And if we do get funding, so getting scintillator made in Russia could be a challenge in the near future. So, but we do want to maybe even develop our own lab to do the chemical coating. Well, necessary. I think this is a contingent upon the available funding. For the smaller scintillator, you can, how big is your scintillator for your cosmic watch? 2 inch by 2 inch?
5 centimeters on the side of it.
And that's about 2 inch square. So have you one thing you can try to turn around up and down. They pretty much the cuts are not changing much. Yeah, because we know the cosmic particles has a cosine and theta distribution. If you point an angle, so you imagine if, for example, if I orient my detector vertically this way, there's a much less cuts compared to the horizontal. So this is one of the reasons we want to have we tried a different technique. Certainly it depends on what the level of the what the goal you want. So I think for high school kids, middle school kids, they can build a detector, assemble, test. It's a great, much fun to do. To use a cosmic watch, right? I think once you started to wanted to make a scientific applications, that I do see the limitations of a cosmic watch.
Yeah, I think you've already commented earlier, and I've done the back of envelope calculations, and you run out of data very quickly. The statistical precision just disappears completely. Yeah, it's great fun, but it's hard to get anything better than 5 or 10%. I think.
Yeah. But I have to stress the phone is also important. Phone is very important because that is where we get our students, engaged.
I absolutely agree. It's a great stepping stone, but the points you were making earlier about being motivated by the science and then building the detectors to get you the precision to be able to do the science. Yeah.
Yes, true. Okay.
We've answered many questions as you've gone ahead through the presentation, which has been really good. Are there any more questions before we close up this evening? No. What a wonderful, stimulating and encouraging talk. We do wish you well, and we'll get you back at some point in the future, near future, to update us on the on the progress of the project. I've been looking for partners in the UK. So far, been not successful, but we will continue to keep our eyes open, because it would be great to have some of your detectors working within the UK, and if we can help facilitate that in any way at all, then we will. We do all we can. We wish you well. We thank you again for sharing with us tonight. Absolutely captivating. I'm not quite sure where the last hour and a half has gone. It's been truly inspirational. Thank you very much, Xiaochun.
Thank you all.
Yes,
okay, great.
Yeah, a standing ovation is what you deserve, but quiet claps is what you'll get. Good night, everybody, and the story of atmospheric physics continues next month. Watch the forums. Take care now. Good night. Bye-bye.
Good night.
Thanks. Bye.
Bye-bye.